So today we'll study about Karatsuba's integer multiplication algorithm. So basically three algorithms we will study. So first, what is the problem that we are solving? So we are solving the problem of multiplying two n-digit numbers. So here the problem is multiply two n-digit numbers. So three algorithms we will study. So first, you already know, you study in your schools. We call it school multiplication algorithm. So you know how to multiply. So and we'll prove that complexity is big theta of n square of multiplying two n-digit numbers. So this is first algorithm we'll study. Now second algorithm, divide and conquer algorithm. Second, divide and conquer algorithm. Again, this will have complexity big theta of n square. Third algorithm is Karatsuba's. Again, this is divide and conquer algorithm. And this has less time complexity. We will prove that this has big theta of n power log of 3 with base 2 time complexity. So before starting our algorithms, I will give an interesting history of Karatsuba's algorithm. So the reference is a paper titled Lower Bounds for Multiplication via Network Coding. The authors are Payman Afshani, Kasper Benjamin Frexen, Lair Kamma, Kasper Green Larson, and this is published in 46th International Colloquium on Automata Languages and Programming, ICALP 2019. So in the first page, in introduction, I will read out the history. Multiplication is one of the most fundamental computational problems, and the simple long multiplication big O of n square time algorithm for multiplying two n-digit numbers is taught to elementary school pupils around the world. Despite its centrality, the true complexity of multiplication remains elusive. In 1960, Kolmogorov conjectured that the thousands of years old big O of n square time algorithm is optimal, and he arranged a seminar at Moscow State University with the goal of proving this conjecture. However, only a week into the seminar, the student Karatsuba came up with an big O of n power log of 3 with base 2 approximately equal to big O of n to the power 1.585 time algorithm. The algorithm was presented at the next seminar meeting, and the seminar was terminated. So this is the history of Karatsuba's algorithm. So first we start with our school algorithm of multiplying two n-digit numbers. So you already know the algorithm. Just giving you one example. The same algorithm we'll use. One, 2, 3, 4 multiplied by 4, 3, 2, 1. So you already know the algorithm. Multiply 1 with 4, we get 4. With 3, we get 3. With 2, we get 2. With 1, we get 1. Next, shift left and repeat the same. Now 2 is multiplied with 4. So here I write we get 8. Then 2 is multiplied by 3, we get 6. 2 is multiplied by 2, we get 4. 2 is multiplied by 1, we get 1. Then 3. 3 is multiplied by 4, we get 12. Again we shift, write 2 here. So 12 we have a carry, write the carry here. 3 multiplied by 3 is 9. 3 multiplied by 2 is 6. 3 multiplied by 1 is 3. Next is 4. 4 multiplied by 4 is 16. Again we shift. 1 is the carry. Then 4 multiplied by 3 is 12. 1 is the carry. 4 is multiplied by 3. 4 is multiplied by 2. 3. 3, 7. There is some mistake. Okay, I will check it. So where is the mistake? Can you point it out? Where? Okay, once again I will check. So 1 we get 1, 2, 3, 4. Oh, so this I will again write it. Yes. So you just get the idea, no need to write it. You know, you already know. So basically we multiply the digits by digit and add the carry. So now the basic idea is we have to count the number of basic operations. So here basic operations we define. Basic operations. So basic operations are multiply 2 digits and add 2 digits. These are the basic operations, and we count the number of basic operations. So again taking the same example, how many multiplications we are doing? You can easily see there are 4 multiplied by 4. So we can just count for multiplication, number of multiplications is 16. How many additions are doing? Again you can see. So can you tell me how many additions we are doing? So just see here, some numbers are written like this, something like this: A, B, C, D, X, Y, Z, W, alpha, beta, gamma, delta, and F, G, H, I, something like this. Add. So number of additions you can see: 1 addition here, 2 addition, 3 addition, 2 addition, 1 addition. So these are number of additions plus carry. We have to also add the carry. So you can easily compute and get the number. So in this case, for example, minimum number is 1 plus 2 plus 3 plus 2 plus 1. So this is 6, 9. So and add carry. So you can have some 3 carries, so 9 to 12. So just writing number of additions, something like in this range 9 to 12. So just add everything. So in total we get 25 to 28. These many number of basic operations. Now same thing we generalize for n digits. So the same thing for n digits. You can easily write number of multiplications is n square, number of additions. So again you get the same series like 1 plus 2 plus up to some n minus 1, then again going back to 1, add everything, plus some additional carries. So carries are not too much. So when you add again, you will get something like big O of n square. So total we get is big O of n square. So this n square is both upper bound as well as lower bound. So you also have small omega of n square, and combine them, you get big theta of n square. Because the number of multiplication itself is n square, so this is the lower bound. Upper bound we have already shown big O of n square, so big theta of n square. So this is the very basic multiplication algorithm. Now the same algorithm we apply divide and conquer. Divide and conquer. So again the idea you know, we have to break the problem into sub problems. So here the original problem is multiply. So here the idea is simple. The problem is, in short, just call it problem of size of parameter n. So here we have to multiply n digit numbers. So we have to break this into small problems. So small problem, this will break into half of the size, parameter half, Pn by 2. So multiply the numbers of size n by 2 digits. So here for simplicity we assume that n is a power of 2. In general, if it is not a power of 2, you can simply append sufficient number of zeros to make it a power of 2. In asymptotic notation, complexity will not change. So this is our simplifying assumption. Assume that n is a power of 2. So at every time you can divide it in problem of size half. So here multiplying two n digit numbers, we have to break the problem into multiplying two n by 2 digit numbers. So again the same example, if we see, you can easily see this, the same example, 1 2 3 4 multiplied by 4 3 2 1. Just break this into smaller parts. 12 multiplied by 100 plus 34 multiplied by 43 multiplied by 100 plus 21. Just apply the distributive law, we get 12 multiplied by 43 multiplied by this much plus 12 multiplied by 43 plus 34 multiplied by 43. 12 is multiplied by 21. Okay, I will correct this. This is plus 12 multiplied by 21 plus 34 43. 34 with 43, this much multiplied by 100 plus, and the last is 34 21. So here you can see we have broken the problem. So here we have 4 sub problems, and the 4 sub problems are 12 multiplied by 43, 12 multiplied by 21, 34 multiplied by 43, and 34 multiplied by 21. So one problem is giving 4 sub problems, and then again recursively again you can apply and break the problem into again 4 sub problems. So this way you can solve this by divide and conquer. So we'll show this in a graph how this is done, all divide and conquer steps, and then find the time complexity of the algorithm. So we start with the original problem. Original problem is 1, 2, 3, 4 multiplied by 4, 3, 2, 1. This is divided into 4 sub problems. The divide step, and the sub problems are 12 multiplied by 43, 12 multiplied by 21, 34 multiplied by 43, 34 multiplied by 21. This is first level of division. The next level, again we proceed. So this is divided into 12 multiplied by 43. Divide it like 1 multiplied by 4, then 1 multiplied by 3, 2 multiplied by 4, and 2 multiplied by 3. So same way others also you can draw. Here we have less space, so we'll continue with only the left branch. Similarly you can make others also. So here now we are at the base problem. We cannot further subdivide, so we conquer, means combine the solution. So the same identity we apply, similar identity at each step we apply. So once we know the products, we can easily combine them. So just we have to perform addition, shift and add, because multiplication by some power of 10 means simply shift, left shift. So just perform left shifts and add. So conquer step is only addition. So just combine all. So first level of conquer we get, combine all these sub problems, and we get the result 516. So same way we continue with the other 3 sub problems also. Break this into 4 sub problems like this each, and then finally combine, conquer step. So here we get at the base at these and conquer the base. So I will draw the continuing diagram, something like this we get. So the second sub problem, 12 multiplied by 21, just combine and apply the same formula, and we get 252. This third sub problem, 34 multiplied by 43, again conquer, shift and add, and we arrive at 1462. 1462. Fourth sub problem, again conquer, 34 multiplied by 21, shift and add to get 714. So these are solutions of first level of sub problems. Now final conquer we do again the same thing, shift and add. So conquer step is shift and add. So finally same formula we apply, just combine all these and get the final answer 5332114. So this way we perform divide and conquer algorithm and multiply 2 n-digit numbers, and this is the divide and conquer graph. Now we'll find time complexity of this divide and conquer multiplication algorithm. So Tn we denote by Tn, time to multiply 2 n-digit numbers. So we know there are 4 sub problems of size n by 2 plus divide and conquer steps combined, they take only linear time. So just write Cn. So this is when the problem can be divided. So you can write this recurrence as, this is when n is greater than 1, and for 1 you can take it as d. T1 just take as d. So again we solve this recurrence using recursion tree method, and idea is same. So just start with the root Tn. So when we continue with this recursion, at the root we get Cn and we get 4 children. 4 children of parameter n by 2. So from this we get this tree Cn, then Tn by 2, Tn by 2 4 times. So again just continue. At the next level, each 4 children will break, leaving root Cn by 2. So next it will become like this Cn by 2 4 times, and then at the leaf level we have T n by 4, having 4. So just like this. So once again just continue this up to the leaf and just simply add level by level. So we have this, we call this level 0. So for level 0 you can count, it is Cn. Level 1 it is 4 times Cn by 2 at level 1. Just continue, you know the pattern, you can easily see. So root we have 1 child, each having weight Cn. Next level we have Cn by 2, 4 children. So pattern you can see, number of children they are getting multiplied by 4, and problem size is getting divided by 2. So very simple pattern, just continue with it. Continue, then we get next level like this 4 square Cn by 2 square. At the second level continue like this. So in general at level I we will have continue like this. So 4 power I Cn divided by 2 power I. This is at level I. Just continue until we arrive at the leaf node. But just before leaf, it is cost parameter is using C. At the leaf it is D. So just continue, and at the final level we will have 4 power log of n with base 2 D. This is at level log n, log of n with base 2. So n you keep subdividing until number of times log of n with base 2 you arrive at 1. At 1 we have cos D, number of children is 4 power log 2 of n. Now everything we have to add to get the time complexity. So Tn we can write Tn is equal to, just take the sum, first level Cn, just perform the sum, 2 Cn, it is geometric series, this goes up to, general term is 2 power I Cn, continues up to just before the leaf we have 2 power log of n with base 2 Cn, and final term is 4 power log of n with base 2 D. So this is a geometric series, you can easily find the sum. So I will just write the simplify the computation. You can fill the steps, something like this. We get 2 Cn, apply the geometric sum, log of n with base 2 minus 1 divided by 2 minus 1 plus, here we get n square d. So 4 power log of 2 with base n, you can write it as square of 2 power log of n with base 2. 2 power log of n with base 2 is n, so we get n square. Similarly here, left part of the expression, we get n minus 1 here. Here we get n minus 1. So just simplify this and get Cn n minus 1 plus n square d. Again, a simple simplification will give you C plus d n square minus Cn, and you can easily write this. There is no need to write the exact constants, just express this in asymptotic notation. We get big theta of n square. So this is divide and conquer algorithm having time complexity big theta of n square. So its time complexity is same as the iterative algorithm. Now next we study Karatsuba's divide and conquer multiplication algorithm. So here we are getting 4 subproblems. So these 4 subproblems make the time complexity n square. So if we can reduce this to 3 subproblems, then time complexity will be reduced. So idea of Karatsuba is divide the original problem into 3 subproblems. So with 3 subproblems, you can easily see the structure of the tree. You will get less number of nodes. So less cost, less time complexity. So next we see how we can divide the original problem into 3 subproblems. This is idea of Karatsuba. So we write our product as, again we break it in 2 parts, but now we will have only 3 subproblems. So write the numbers as like this. High part, first half of the part, write it as h1 multiplied by 10 power n by 2, low part L1. So original number we divide in 2 parts. Second number also same way, h2 multiplied by 10 power n by 2 plus L2. So again same expression we get, there is no difference, h1 h2 multiplied by 10 power n plus h1 L2 plus L1 h2 multiplied by 10 power n by 2 plus L1 L2. So this way we get 4 subproblems. Now we rearrange, we use different expression, and the different expression that we use is write like this, h1 multiplied by h2 multiplied by 10 power n. So high part we keep it as it is, low part also we keep it as it is, L1 multiplied by L2. Now the remaining subproblems we combine in a different way, so we use different expression, and the expression is this plus h1 plus L1 L1 multiplied by h2 plus L2 minus h1 multiplied by h2 plus L1 multiplied by L2, this multiplied by 10 power n by 2. So now you can see how many subproblems are there. First is h1 h2, second is L1 L2, it is reused in the second expression, h1 h2 plus l1 l2. Third subproblem is h1 plus l1 multiplied by h2 plus l2. So this is the simplification we use. Now we have only 3 subproblems. You can easily see, just expand these. On simplification you will get here h1 l2 plus l1 h2, which is exactly the expression we want. So now we have only 3 subproblems and our complexity is reduced. So first we will see, using the same example, how to make divide and conquer graph, and then find the time complexity. So once again we take the same problem and make the divide and conquer graph. So the original problem is 1 2 3 4 multiplied by 4 3 2 1. Now we have 3 subproblems. What are the subproblems? So the first subproblems is multiply the high parts. So we divide like this. This is h1, this is l1, this is h2, this is l2. So first subproblem is multiply the high parts, h1 h2. 12 multiplied by 43. 12 multiplied by 43. Second subproblem is multiply the low parts, L1, L2. 34 multiplied by 21. Third subproblem is, just see the expression, h1 plus l1 multiplied by h2 plus l2. So we have to add, for each number just add high and low parts and multiply them. So for 1 2 3 4, high and low parts are 12 and 34. Add them, we get 36. 46. So h1 plus l1 is 46 multiplied by, for second number 43 plus 21 is 64. So now we have 3 subproblems. Again continue like this. So for a sample we can take this second problem. So just take this 34 multiplied by 21, again apply the same idea, divide this into 3 subproblems. Again here we have high part, low part, h1 l1, h2 l2. So again we get 3 subproblems. So first subproblem is multiply the high part, 3 multiplied by 2. 3 multiplied by 2. Second problem is multiply the low parts, 4 multiplied by 1. Third subproblem is add high and low parts for each number. 3 plus 4 is 7. 7 multiplied by 2 plus 1 is 3. So this is the base problem. We cannot further subdivide. So same way we continue for others also, like this. So finally we combine. How we combine? We know the formula. So how to combine? So 3 multiplied by 2. Again same thing, shift plus add. 3 multiplied by 2 is 6. So how we combine that? Just giving one example. 6 multiplied by 100 plus L1 L2. L1 L2 is 21 plus, again see the formula, This is third subproblem. Third subproblem minus the sum of first and second subproblems multiplied by 10 power n by 2. So here the third subproblem is 7 multiplied by 3 is just correct this 4. This is second subproblem is 4. So 600 is h1 h2 multiplied by 100. L1 L2 is 4. This is 4. Now for the remaining we have third subproblem minus the sum of first two subproblems. So this plus 6 plus 21 minus, so here write 21 minus, this is third subproblem, the sum of first two subproblems, 6 plus 4 multiplied by 10. So multiplication by 10 or 100 is simply left shift. So here you can see we are simply performing addition in the conquer step. Now just simplify this, we get this is equal to 604 plus 21 minus 10 is 11, 110. Add, we get 704. Correct. 714. So here just write the result 714. So same way we conquer the other subproblems at the first level and make the graph. So I will just write the answer. So we get 516 by combining these three. So here this third subproblem, if we expand, you will see it will have some extra level of nodes. Why? Because of this expression. This expression can make the problem size slightly larger than half. So you can make the complete tree. So I will just write the final result. Combine these values and get 2944. So once again at the final level of conquer step, again shift and add. You already have the results. Shift 516 sufficient number of times, add 714. Third subproblem minus the sum of the remaining two subproblems multiplied by shift sufficient number of zeros, add everything. So conquer step is basically shift and add. Again we combine all these results, combine all three and get the final result using the same idea. 533 2114. So now we'll find time complexity of this expression. So detailed time complexity I have written in my lecture note, you can read. So in short you can write it as, now we have Tn is equal to, just write it as 3. We are getting 3 subproblems, 3 Tn by 2, 3 subproblems of half size plus divide and conquer step, they take only linear. Write it as Cn when n is greater than 1 and write it is as equal to D when n is 1. So again same idea, but the only difference is this time number of subproblems is 3. Same idea, similar idea we use. So this time we get similar tree structure but with 3 children. So Tn becomes root, we get Cn 3 sub problems we get Tn by 2. Again, next level we apply, we get Cn, 3 sub problems, size is Cn by 2 each. And next level is Tn by 4, 3 children of each. So same idea, just add the cost at each level and add everything. So 0 level we are getting Cn, size is getting divided by 2, number of children is getting multiplied by 3. So net effect is 3 by 2. Next level we get multiplied by 3 divided by 2 Cn. Next level it's square, 3 by 2 square Cn. This continues until root. So just before root the constant used is C, at the leaf constant used is C, D. So again similar computation, continue like this. So general term we have at level I we have 3 by 2 power I Cn. At the final level we have D multiplied by 3 power log of n. Now add everything, we get a geometric series, add, we get similar expression. So Tn we write Cn plus 3 by 2 Cn plus goes up to 3 by 2 power log of n with base 2 minus 1 Cn. Last term is 3 power log of n with base 2 d. So I will just write the expression. Apply the geometric series Cn 3 by 2 power log n with base 2 minus 1 divided by 3 by 2 minus 1 plus n power log of 3 with base 2d. So just simplify the expression, final expression I will write. We get something like 2c plus d. Now power has changed because the factor now is 3 by 2. So after simplification power we get is log of 3 with base 2 minus 2cn. So again there is no need to keep the constant, write in asymptotic notation. So we get big theta of n power log of 3 with base 2 and approximately equal to n power I have already described. It evaluates to something 1.585. 1.585. Any questions? हाँ